Hey, Wheat North, Mr. Yergler here. There's two powerful models that we use to help us understand the shape of molecules and how they bond and how they are structured. One of them we've already talked about, the Lewis dot structures. And these help us kind of arrange and assign electrons around an atom, around the atoms. But the other one is called the VSEPR theory or VSEPR model. And now that we've done Lewis dot structures, we can now talk about VSEPR model and molecular shapes. VSEPR stands for valence shell electron pair repulsion. It kind of looks like it should be pronounced VSEPR, but everyone just says VSEPR. This is grounded on the fundamental understanding that the shape of a molecule is determined by the electron repulsion. It's basically Coulomb's law at work. So because electrons all repel each other, and these electrons are arranged in pairs around the central atom, they can only exist in certain arrangements because they're going to repel each other as much as possible. And just as a side note, lone pairs repel more than bonds, and this is because they take up more space. They're a little bit less. The electron clouds are a little bit less dense when they're just lone pairs because there's no other nucleus that they're pulled towards, and so they just kind of hang out in this electron cloud. Okay, so to determine the shape, we can use any resonance structure because resonance structures pretty much always have the same shape. You're just moving the location of a double bond. And remember that the double and triple bonds count as one bonding domain. And what I mean by a bonding domain is essentially a location around the central atom where there's electrons. And if there's no central atom, then it's not a classified shape. Okay, and I'll come back to that in a second. This picture helps us understand what we mean by a bonding domain. The nitrate ion has one double bond, and so this is kind of showing the third of a double bond that each oxygen has when it's in resonance. And so the bond order of nitrogen in this case would be like 1.3. There's only 3 bonding domains on this nitrogen atom, on the central atom, because there's only 3 places where there's electrons. That's what I mean by bonding domains or electron domains. Sometimes there's no one central atom, and so we don't classify it as a particular shape. This is a good example. There's no shape that can be assigned to this whole molecule. We may say that this particular carbon atom at this point here has a shape, which would be trigonal planar. So one atom could have a shape around it, but we don't assign a shape to the whole thing. All right, so here are the possibilities for electron domains. It can be anywhere from 2 up till 6. If there's 2 electron domains on the central atom, that is, again, 2 places where there's electrons, then it's a linear shape, and this kind of makes sense. Essentially what we're saying is these electrons in each bond, there's no reason for them to be next to each other. Like this hydrogen is not going to swing around here because the electrons repel each other, so they're going to get away from each other as much as possible. So they're going to form a linear shape. If there's 3, they form what's called a trigonal planar shape. This picture shows it really well. It's going to be a 120-degree bond angle, and that's as far away as they can get from each other. Essentially, it's a 360 divided by 3. Even if there's a lone pair of electrons, this is still 3 electron domains, right? 2 of them are bonded, 1 of them is unbonded. The electrons are still in a trigonal planar shape. The molecule has a different shape, which I'll get to in a second, but the electron geometry is still trigonal planar. All right, tetrahedral is if there's 4. This has a 109.5 degree bond angle. And remember that lone pairs repel a little bit more than bonding pairs, and so if you have a lone pair up here, it kind of changes the angle of that a little bit. Well, so it's be a little bit less than 109, but roughly 109 degrees is acceptable. Once we get to this point, we start introducing the third dimension, and it's helpful to kind of picture balloons. Imagine pinching together 4 balloons. They're gonna kind of push off of each other equally in all directions, and so they form. If you have only 3 of them, they would form like this trigonal planar shape, but if you introduce the 4th, now one is coming at you and one is kind of pushed back behind, and this is like a tetrahedral shape. They're all pushing off each other equally. I like to think of this as a way to kind of understand how they repel each other and how they would arrange themselves. If there's 5 electron domains, then it's trigonal bipyramidal. Ammonia is a good example of a tetrahedral electron geometry, but a different molecular geometry. This nitrogen atom still has 4 electron domains around it, right? So it's still going to arrange itself in this type of structure. When we draw the Lewis dot structure, it looks like these kind of form 90-degree angles, but in reality, remember, it's in 3 dimensions, and so this lone pair of electrons is going to repel these bonding electrons and kind of push them at a downward angle. It's still going to be about 109 degrees, a little bit less, because the lone pair repels more than the bonding pair does. but it's still a tetrahedral electron geometry. All right, now let's move on to 5. If there's 5 electrons, again, the electrons are just getting away from each other as much as possible. This is the only type of arrangement that maximizes the distance or the angles between all the electrons. Notice that there's 2 different angles here. This is kind of shown in this picture. These have a 90-degree angle, but these ones have a 120-degree angle. Picture a linear molecule kind of superimposed over a trigonal planar molecule, right? That's kind of what this is. It's a mix of trigonal planar right here and then linear right here. And the name comes from the fact that when they're in this arrangement, they're essentially forming 2 pyramids, right? One on top and one on bottom. All right, the last one is when we have 6 electrons. This is as large as we're going to get, and this is called octahedral. So essentially we've taken that trigonal bipyramidal and we've just kind of jammed another pair of electrons in there. And now we have 90-degree angles between every bond, no matter where we look. Now let's get into this electron versus molecular geometry. This is an important distinction. The electron geometry I just went over, those are the only possibilities, but we can have additional possibilities when we talk about the molecule itself. So if we have a trigonal planar electron configuration, but we have one lone pair, the electrons are trigonal planar, but because there's only atoms in 2 of those 3 locations, the molecule forms a bent structure, right? When we're looking at the molecule, we don't consider the lone pair as part of the shape of the molecule, right? The molecule is bent, but the electrons are in a trigonal planar arrangement. So very important distinction. This is the electron geometry. This is the molecular geometry. The next one is tetrahedral. If we have one lone pair with tetrahedral, then it's trigonal pyramidal. If there's 2 lone pairs, it can be bent. So there's actually 2 different ways that we can have a bent molecule. Here's pictures of each of those. This is like that ammonia that I showed you earlier, trigonal pyramidal, and then bent. If water is a good example of that. 2 lone pairs forces it to be bent. We're just replacing one of these atoms with a lone pair. So it's the same overall structure, but because we've removed an atom, the molecule itself has a different shape. Trigonal bipyramidal, if there's 1 lone pair, it's called a seesaw arrangement. If there's 2 lone pairs, it's called T-shape. If there's 3 lone pairs, it's called linear. And this is just logic. I don't really want you to necessarily memorize this. If you just know what trigonal bipyramidal is or what it looks like, and you imagine 1 lone pair, you can tell that there's going to be your linear and then 2 kind of sticking out, and that's going to form like a seesaw shape. Same thing with T-shaped. If we have 2 lone pairs, then we have essentially a T. Imagine this kind of rotated 90 degrees. And then linear. Now, the electrons repel each other more than the bonds do, and so the electrons take this 120-degree location, whereas the atoms take the 90-degree angles. So we have a 90-degree angle here, but 120-degree angles between these. Last one is octahedral. If there's 1 lone pair, it's called square pyramidal. If there's 2 lone pairs, it's square planar. Here's our octahedral structure. If we have only 1 lone pair, then we have a square, essentially, with a peak, hence the name square pyramidal. And if we have 2 lone pairs, again, they get away from each other as much as possible. The lone pairs are not going to occupy adjacent locations because they repel each other more than the bonds do. And so we have like a square shape right here in one plane, so square planar. Those are all the different combinations of molecular shapes and electron geometries that we can have. A lot of it is just practice and then doing the Lewis dot structure and kind of figuring out which one matches the right shape. Here's a couple of examples. Do these in your notes. Give the Lewis dot structure and then identify the shape and give the bond angles for each of these. Bring any questions you have to class. We'll go over these in class and kind of get some more practice. All right, this is Mr. Yerkler signing off.